Hello everyone, this is another video relating to the book Introduction to Probability, second edition by Blitzstein and Huang. Remember, you can download the book from the internet, so you do not have to buy a hard copy in order to enjoy learning from it. So today's topic is conditional probability. Now, conditional probabilities are probabilities, so the things we've said about probabilities will be true for it, but it's a probability that is conditional upon some other event. In this case, we're interested in the probability of event A conditional on event B. Now, maybe we're interested in this because we have found that B has happened, or we believe that B is true, but maybe we're just kind of thinking, well, what if? Maybe it's hypothetical. Maybe we're pretending. Anyway, a conditional probability treats B as though it were true, but we may or may not actually think that when we are using conditional probabilities. If we understand probabilities, then we can define conditional probabilities using this formula here. We have the probability of the intersection of sets A and B. And down in the denominator, we have the probability of B, which is this second thing here, the thing that I'm conditioning on. So this is not an event A given B, this is an event A that we're interested in the probability of, given or assuming the occurrence of event B. Now, if we introduce the pebble world that Blitzstein and Huang use, we can do some conditional probability calculations quite nicely. So recall they have 9 pebbles, and then they have 2 sets, A and B, and their sets are not exhaustive and they're not mutually exclusive either. So they're complicated enough to be interesting, you might say. So here is set A. It looks like this with these 5 pebbles. And then here is set B with these 4, and this is at least sometimes blue. So B tends to be blue. A they mark off in red. So now we can start taking a look at this picture, and we see this little square in here, this pebble, is the intersection A intersection B. And so we want the probability of that. Well, it's only 1 pebble out of 9 in our sample space, isn't it? So we have the probability of A intersection B equals 1 over 9. We also need the probability that's in the denominator, P of B, and we get that by noticing we have 4 pebbles in B out of the whole sample space of 9. So our probability of B is 4/9. And if we stick these numbers into here, we see our numerator is 1/9, and our denominator is 4/9, and therefore our conditional probability of A given B is equal to 1/4. Now, another way to see that is simply to assume that B is like our new sample space in a sense. We pretend that B is all there is, and we say, of these 4 pebbles, how many are in A intersection B, which is just this 1 pebble here. So it is, again, 1 pebble out of 4. So whether I just restrict my attention to B and count, or whether I think of A intersection B and B as subsets of the original sample space, I get the same answer of 1/4 either way. Now, there are other conditional probabilities I could be interested in. One of them is, one of the most interesting in fact, is the probability of B given A. Now, we haven't really said anything about what B or A mean. We'll do that before long when we start talking about Bayes' theorem. But here we're simply giving the two sets different roles. Now, I can use the same formula as I used up here, but I want to switch A and B. Now, A intersection B is the same as B intersection A, so switching that doesn't matter. So I'll switch them, and then if you like, switch them around again to get back what I had, since it doesn't matter. But the denominator is now P of A, isn't it? Now, once again, we can take both of these as fractions of the original sample space, or as so A intersection B is has a probability of 1/9 in the original sample space, while A has a probability of 1, 2, 3, 4, 5/9. Therefore, this conditional probability is equal to 5/9. So you will notice these are clearly not equal to each other, which is a clue. Well, sorry, of course I should be drawing that to here. These are clearly not equal to each other, which is a clue that they also have quite different meanings. If they have different values, and clearly they have to have different meanings. So we need to work hard not to confuse them, and sometimes people do confuse them. We will see that we give quite different roles in Bayes' theorem to different conditional probabilities depending on how we interpret our sets. So that will be a big step in our using probability as a sort of Swiss Army knife of reasoning in shades of gray, if you will. Maybe I'm mixing my metaphors, but I think you know what I mean. Okay, so here's an example. Involves a deck of cards, standard deck, 4 suits, 13 ranks. So we're going to draw 2 cards, one at a time, without replacement, so the first card is not there when I draw the second card. And let's let A be the event that the first card is a heart, and B is the event that the second card is red. So given my formula for these conditional probabilities, I'm going to want to start with the probability of A intersection B. What happens if these events are both true? First I get a heart, then I get a red card. Well, I can start, of course, with the heart since it comes first. I don't have to, but I certainly can. And there are 13 hearts out of 52 cards. Now, since we've already said A occurs, we know that the first card was a heart, and therefore 1 heart is missing. So our deck has 25 red cards left out of 51 cards left. So our probability of getting a red card for our second draw is, well, of course, we can simplify the 13 52nds to 1/4. Now we can also notice there are 4 suits, they're all fully represented, so we could just cancel out the factor of 13 to start with, and then our arithmetic gets a bit easier, so our probability of A and B is 15 over 204. Now, we mentioned that any suit has a probability of 1/4, so since A is that the first card is a heart, that must be 1/4. Now B, that the second card is red. Well, this one's a little bit tricky because this doesn't say the second card is red given that we've already taken away the first one. I mean, we don't know if A has happened or not. Maybe the first card was a heart. Maybe the first card was a club or a spade, which are the black suits. So when I'm asking about the second card here, I need to make sure I'm not assuming that the first card was red. So basically, I don't know anything about the first card. Maybe I drew it and then hid it somewhere without looking at it, and then I've got 51 cards left, but I don't know whether I'm a little bit short on red cards or I have got a slight excess of red cards after that first draw, or slight majority. So my probability of B here basically can ignore all of that, and since we have no idea what happened with the first card, so my probability of getting a second card that is red is simply 1/2 by symmetry. So you might be tempted to take away that first red card, but we have to make sure we don't do that. Okay, so we use symmetry to get a half, or you could think there are 26 red cards that are hence favorable and 52 cards. So you could get 26 over 52, which of course is the same thing, only a little more complicated. All right, now we are ready to calculate some conditional probabilities. So the conditional probability of A given B now, you might think, how is it that I don't know about the first event and I already know about the second one? Well, you could think of situations in which that might occur. So these conditional probabilities are not always things that you would easily think up as describing real physical situations, but they do wind up being quite important in our reasoning in various indirect ways. Okay, so the probability of A conditional on B has this expression here. Here's our formula, and we've got our values. 25 over 204. Then the probability of B is 1/2. So if I divide by 1/2, that's the same as multiplying by 2, isn't it? And then I can cancel, so that's 25 over 102, which is close to a quarter, but it is not exactly a quarter. And the probability of B given A will be the same numerator. Recall, we can flip the A and B around, but then everywhere, but then since the intersection is symmetric, we can flip it back without any cost. And then we'll have divided by the probability of A here. So we will get 25 over 204 divided by 1/4, which means times 4, doesn't it? So that's 25 over 51. Now you could think of the probability of A given B as saying, forget all about everything in your sample space that is not part of B. And recall, B was down here, right? So we just forget about all these other events. And then we had this one here that was in A intersection B. So it's like we forget about everything other than B, and then we just, we're conditional. All our probabilities are now conditional on B. So, that is how you would get that kind of thing. Or you could, if you prefer Venn diagrams with ovals, you could think of A for this left oval and B for this right one. And then there's their intersection, which is in here. Now, this intersection you could think of as a certain fraction of the A circle. So here's a fraction. But then if you want the whole thing, you might multiply by the A circle. So this first, this expression here is the conditional probability, and it is the fraction that this colored region occupies of this circle A. On the other hand, we could also write the fraction that A intersection B is of B. So now I'll be directing my attention to circle B, and I'll say this shaded region divided by this whole circle B is of interest to me, and that fraction is my conditional probability. But then if I want the whole thing and not just the fraction, then I multiply again by probability of B. And of course, these are both equal to the probability of the intersection, and hence these two are equal to each other. So this is a graphical way to see this expression here, which is basically just two ways of writing the probability of A intersection B. So there we go. We can focus our attention on one circle or the other, and then we get one fraction of one circle or another fraction of another circle. And then we can see how we get the same result both ways.